Kerswell is going to tell us a little bit about what he's been working on in his postdoc for this for the last year.
Thank you very much. Yeah, thanks, Dave, and thank you all for being here on a Friday. Title of my talk is Displaced and Faded. And no, I'm not talking about the last time John and I got kicked out of the AJ. That admittedly is a better story to tell. It's probably more exciting than the one I'm going to tell today. Today I'm going to tell a story about mantle dynamics and phase changes in Earth's mantle, and how thermodynamics and kinetics of those phase changes significantly impact the seismic structures of Earth's mantle. So, seismologist, I'm not a seismologist, but I read seismology from time to time. And the geophysicists produce lots of figures like this. And basically what they're able to do is listen to seismic waves or teleseismic waves that travel through the Earth from some earthquake. And they bounce off of these layers in Earth's mantle. And then they reach some receiver in some other part of the Earth. And depending on how long it takes those waves to go from the source to the receiver, they can effectively estimate the depth at which these things bounce off of whatever they bounce off of. And they give us pictures like this. So on the top left is a measurement or an estimate based on geophysical observables of the depth to the 410 to the 410 seismic discontinuity. The 410 seismic discontinuity you can just think of as where there's this significant density increase in Earth's mantle. And it relates to a particular phase change when olivine, the mineral olivine, breaks down and forms effectively a denser form of olivine. Right? So seismologists can measure the depths of these things and they produce this map. They also measure the depth to another significant discontinuity in Earth's mantle located at approximately 660 kilometers depth. Again, that relates to an olivine-like mineral transforming to form a more dense phase. In this case, it forms two phases. And then, you just take the difference between the 660 and the 410, and you can get some estimate of the thickness of what they call the mantle transition zone, the MTZ, the mantle transition zone. Transition zone between Earth's upper mantle and Earth's lower mantle. And in some regions, the transition zone is a bit thinner, and in other regions, it's a bit thicker. And because these phase transitions, they're mostly pressure sensitive, but they are a bit temperature sensitive as well. So you would expect the depth of these phase transitions to change if there's something very cold or if there's something very warm in Earth's mantle. And so if you sit back and you kind of squint your eyes and you look at these figures, you'll see that, okay, the mantle transition zone is a bit thicker in the northwest Pacific, around Southeast Asia, down to Papua New Guinea and to New Zealand. This is where we have lots of subduction. So this cold material, cold oceanic lithosphere is subducting in these regions. Same case for South America. So it's a bit thicker over here. Same tectonic story. And then we have these hot spots in the Central Pacific and then the South Pacific where the mantle transition zone is a bit thinner. And it's because presumably there's warm thermal plumes in these regions, right? That's the general story. But then you look at other regions in the Earth, like Cascadia, where there's a subduction zone, but you have the opposite relationship. And also in the Caribbean and other places, where the story starts to sort of break down. Okay, we no longer are just relating cold things to thick transition zones and warm things to thin transition zones. So there has to be something else going on. John showed this cartoon last week for those of you who were here. But the geophysicists produce like cartoons like this sometimes in their work. And they're trying to explain what they observe in terms of the depths and the thicknesses of the transition zone. So here's the 410. It's nominally at 410, this depth here. This is 660. It's nominally at this line. And notice how they draw it with a sharp line, by the way. always draw the sharp line, because that's what equilibrium thermodynamics would predict. These minerals just react more or less instantaneously. You just go from one to the other. And they note here that, okay, if you have more material that's upwelling, you might slightly move these phase transitions. Same case for a hot spot. You might move these phase transitions. If there's a warm plume that's going up here, notice how the transition zone itself gets a bit thinner because the 410 gets depressed and the 660 gets elevated slightly. And then, of course, the opposite story for a slab. So if you have some cold slab going down, the 410 is going to do the opposite. It's going to be a little bit elevated, and the 660 should step down a bit just because it's interacting with this cold material. But what about the cases where that doesn't hold? So then this opens up a bunch of different hypotheses. So the geophysicists and the petrologists will argue to the ends of the earth about things like water in the mantle, melt in the mantle, or perhaps some different phase transitions that might explain these sort of oddball cases, these edge cases. Right? So thermodynamics alone can't explain all of the seismic observables. It gives us some rough correlation, but it doesn't explain every case. Meanwhile, we know that these phase transitions are rate limited. Okay? They measure this in laboratories. Here's an example of how they do this. They get this nice starting material, a bunch of olivine, and they anneal it. So it's got these really beautiful triple junctions. Not a lot of defects, but there are some. And then they put it in a press, basically, and they jack up the pressure, jack up the temperature to the point where the olivine starts to break down. And what you get, which is shown by the little white arrows here, is little nuclei, little micrograins of the denser phase, wadsleyite, that forms at the grain boundaries, at the triple junctions, but also within the olivine grains themselves. If there's enough dislocations and defects, they can start to grow within the olivine grains. This is a color EBSD map that shows in yellow these little micronuclei of the dense phase wadsleyite. You can see it starts to form really quickly, actually, this interconnected network of little nuclei around the grain boundaries. When that nucleation takes over and you basically saturate all the nucleation sites, these interfaces start to move towards the center of the olivine, consuming more and more olivine, making more and more wadsleyite. And if you were here last time, this is kind of the process that Lucy was modeling at a very micro scale. Now, it's pretty crazy, but they can actually measure the rate of this transformation in the laboratory using X-ray diffraction. Right, so we have some empirical data about how fast this process happens. Now, John and Lucy and I were working on this grant, and the broad scientific question that we're trying to address is this one. What is the impact of stress, these microstructures, and these small scale, mineral scale kinetic factors? What is the impact of these different processes on macro scale, mantle scale dynamics and seismic structure? And we're all taking a different approach to this problem. We're all taking a different crack at it. The hypothesis that I've been working on is effectively this. We think that it's possible that variable rates of this olivine to wadsleyite transition, so variable growth rates in slabs and in plumes, can explain the edge cases, let's say. They can explain the displacements and the seismic signals that are not fully accounted for by equilibrium thermodynamics alone. That maybe it's something to do with the reaction rates. So how do we go about testing this? Because of course we can't just get ourselves into the mantle, take a look around and make measurements, right? So my approach to these types of problems is to use numerical techniques. These are physics-based simulations of mantle convection. In this case, we use a program. It's called Aspect. It stands for the Advanced Solver for Planetary Evolution, Convection, and Tectonics. So it's sort of a specific made software that uses a finite element approach to solve these equations of, well, these equations describe the flow of Earth's mantle. This equation is called the Navier-Stokes equation. It describes the force balance between pressure gradients, deformation, and a buoyancy force. So hot things rise buoyantly in the Earth's mantle, cold things sink buoyantly like a lava lamp. It's kind of what this equation describes. This equation describes the conservation of mass. So if there's stuff that's advecting around, if there's a mass flux, that has to be balanced by the change in density over time. So this equation accounts for both the mass flux, so moving fluid from one part of the mantle to the other part of the mantle, but also it accounts for phase changes in this term. So if one phase reacts to form another phase, there's a change in volume, and if there's a change in volume, there's a change in density. And then this equation here describes heat, thermal energy, where it's going, where it's being generated, where it's sinking, and so forth. And I've highlighted the density term here because what typically happens in these types of simulations is you make some assumptions. You make some assumptions that make these equations easier to solve numerically. The assumption that we typically make is we say, okay, everything's incompressible, meaning that the density doesn't change over time. So we're going to ignore space changes and we're going to ignore any sort of thermal expansion or compressibility. It turns out that that significantly simplifies this part of the equation, it simplifies this equation, and everything just becomes easier. We use Aspect because it's the only open source, widely available software that has a novel approach to simulating a compressible mantle that takes into account volume changes and density changes, both due to phase transitions and also heating and cooling. Okay, so this software we use because it has this sort of novel approach. It allows us to simulate what we want to simulate. It allows us to look at phase changes and the effects of temperature on the mantle flow. The thing that we've added to Aspect that's new, kind of, is we implemented this kinetic growth rate model into Aspect. So now instead of assuming that when olivine transforms to form wadsleyite in these simulations happens instantaneously, which is what most people assume, it follows hydrostatic equilibrium, thermodynamic equilibrium, we're instead going to move beyond that assumption, and we're going to directly implement this pressure and temperature dependent kinetic rate law into the software. And this hasn't been done for the first time. So this is not technically novel. People did this in the 90s. They did this in the 90s. And if you look at their paper, it is like, I've read these papers and you cannot make heads or sense of like how they actually did this, right? This was just like purpose-built software that they just smashed together to look at what happens in slabs as they go down and you're forming, you know, wadsleyite from olivine, right? So it's not technically new. People have done this in the 90s, but for the first time, it's now available in a widely distributed, well-known geodynamic code that like people actually can go and use, right? So already, I think this is a significant contribution coming from this work. All right, so the rate law itself. The rate law itself describes the change, ignore this little dot, the change in big X, where big X is the volume fraction of wadsleyite in the mantle. So the change of the volume fraction of wadsleyite with respect to time. Okay, so how fast you're forming wadsleyite is a function of some kinetic factors, Z, which include things like the grain size, this constant A, which is sort of a material constant, and the concentration of hydroxyl, or in other words, the amount of water that you have in the rock. Right, so these are all kinetic factors. Then there's this Arrhenius term here that describes the exponential dependence of the reaction rate on temperature. So if you crank up the temperature, the reactions proceed really fast, right? And vice versa. There's some activation energy here as well. This term here describes the thermodynamic driving force for the reaction. So the reaction is not going to proceed. This in parentheses here takes a value from 0 to 1. If delta G is negative, the reaction proceeds. If delta G is positive, there is no reaction because there is no thermodynamic driving force behind that reaction. Okay? And then this last term here is a saturation term. So if you've already formed 100% wadsleyite, there's no more wadsleyite to be formed, right? So the reaction naturally shuts itself off as you form more and more product phase. Delta G itself, and I think this part may be novel, I'm not sure actually, John, but delta G itself is a function of pressure and temperature, but this is not hydrostatic pressure and temperature. In the numerical software, it gives you some reference pressure. This would be like the reference pressure in the mantle if the mantle was not moving around. But we know that the mantle is moving around. And in the software, what it actually calculates is what they call the full pressure, right? This is what's actually moving the fluid in the simulation. But there's some sort of reference state that we look at, and then we calculate what's called the dynamic pressure, which is just the difference between the pressure that's moving the fluid around compared to what the pressure should be if the mantle was perfectly still in its hydrostatic state. Okay, so we have some kinetic factors. There's a temperature relationship here. There's a thermodynamic driving force that not only depends on hydrostatic state, hydrostatic pressure, but also on dynamic pressure and the dynamic temperature. And then there's a saturation term. This is what we've implemented into aspect. Okay. These pictures here, this one for a slab. Imagine a cold thing coming down from the top. And then this one for a plume, imagine a hot thing coming from up here. This is just showing you that thermodynamic term, the driving force. So notice up here, it's all white. This is where delta G is positive. We're in all the instability fields, so no wadsleyite is forming. It's not stable. And as you go down into Earth's mantle, you cross this nominal reaction boundary here. This is where hydrostatic thermodynamics would tell you olivine goes to wadsleyite right here. And as you go further and further from that reaction boundary, you get more and more and more thermodynamic driving force, which is going to make the rate go faster and faster and faster, as long as there's still olivine to be reacted in the rock. But look what happens, because you have a cold slab going through here, these reaction boundaries now start to move around because they're temperature sensitive. Okay, so I implemented this at the Aspects Group Hackathon this year. They invited me out. I told them I have this idea. John really had the idea, right? He just asked me to do it. And then I told the Aspect folks, they said, we'd be happy to have you out there. They invited me out to the hackathon. It just happened to be in the state of Utah where I grew up, which was nice for me because then I could stick around and spend some time with my family this summer. Aspect itself is this big, large open source project. So there's lots of contributors and they're very, very welcoming. It's the first time I've ever done anything like this ever, right? Contributed to like a big software package. So I was a bit intimidated, a little bit nervous. They were really super helpful. It's funded by these three groups mainly, but then there's loads of students and postdocs and people who just contribute code to this project and they're funded by their own universities and their own grants. They set it up in this nice like barn. And so basically we just spent all day coding and like eating really good food, which was nice. It was in Bear Lake, Utah. So of course we went hiking in the Wasatch Mountains. This is a nice shot of these folded Paleozoic limestones. So we did get a bit of geology. Beautiful in June. Absolutely gorgeous. And then I found this nice piece of American steel in the garage. So I helped myself and I took it out on some trails and that was really nice too. Looking for black bears. So, we have, fun as we do science. Can do both. Okay, so now I want to show you some results. So what did we find from our simulations? And John actually hasn't even seen this yet because I've just redone all this work in the last few days because John asked me to change some boundary conditions, right? So I'm going to be here gesticulating a little bit, and I'll be taking some cues from John to see if he approves or not. Okay. Here's a slab, right? Slab's coming down from the top. The color shows the thermal anomaly. So what is the temperature relative to the background temperature, relative to the reference state temperature, right? So there's this big cold anomaly. It's coming down here. The reaction happens somewhere roughly here. This middle panel is showing you the what I would just call the dynamic density, which is the difference between the density of the background mantle versus the actual density that's being solved for numerically. And so you can see, because the material is cold, you can see it's a slight blue color here. It means it's slightly more dense than the background mantle. So it's going to have this negative buoyancy force, right? This thing, because it's cold, it wants to drip down. It wants to go towards the bottom of the mantle, bottom of the model. But it's starting to react as it passes through this phase boundary, and it starts to form this olivine layer. And because the olivine is slightly less dense than wadsleyite, there is this positive buoyancy force that is starting to sort of impede the downwards motion of the slab. Because the reaction doesn't just proceed instantaneously, but it actually takes some time to react the olivine, you get metastable olivine in the wadsleyite reaction field. Right? And this is changing the mantle dynamics because now the slab is stagnating. Notice it's not going through this boundary. It starts to stagnate here because it's got this massive metastable olivine buoy basically beneath it. And then look what's happening to the seismic structure. This is the pressure wave velocity in kilometers per second. So normally the mantle would have a sharp transition here. You can see the colors change sharply here. But because you have this slab, this cold material with sufficiently slow reaction rates, sufficiently sluggish kinetics, you get a bunch of metastable olivine that's not only depressing the 410, so it's moving the seismic discontinuity down, but it's also fading it out. So the gradient is becoming weaker as well, right? So if you have sufficiently sluggish kinetics, you not only are affecting the overall dynamics of the slab, but you're significantly impacting the seismic structure. So what happens if you crank up the kinetics, right? So we just increase those kinetic factors in the equation. We can do that because it's just a simulation, right? So let's just see what happens if you just increase the reaction rate. By the way, how much time do I have? 50 minutes? Okay. So let's increase the reaction rate and notice what happens. The dynamics change, first of all, so the slab just penetrates through the phase transition. It penetrates through the phase transition because no longer is this massive metastable olivine buoy underneath here, but actually the opposite happens. This is what you would predict if you were working under assumptions of thermodynamic equilibrium. You'd actually predict because the slab is cold, it's going to stabilize wadsleyite above the nominal 410. It's going to create this positive, more dense, so it's going to create this downwards negative buoyancy force that's actually going to promote the slab penetrating through that 410. And then we see a very sharp seismic discontinuity with a little bump, but it's sharp everywhere, right? Now, if you take a line, if you take a center line through this model, and you measure the reaction rate through this line, and you measure the width of this discontinuity and its displacement, you can look at these on sort of a bivariate chart here. So these charts, what they're showing is the relationship between the reaction kinetics, so how fast is the reaction proceeding, and the structure of the seismic discontinuity in terms of its width, how thick it is, and also where it is on a vertical axis. Okay, so the first one shows PTZ is phase transition zone width. In other words, the seismic discontinuity width. The width at which olivine reacts to form wadsleyite. And on the x-axis is the displacement. So where does that reaction happen in a vertical sense? Both positive and negative. Reference to the nominal 410, right? So on the x-axis, zero displacement means the reaction happens at 410. And on the y-axis, if the reaction is sufficiently fast, approaching thermodynamic equilibrium, we would expect it to happen at 0 on the x-axis and somewhere in this region, meaning that the transition is also sharp. So we have a bunch of simulations that fall within this region, which I'll just call, approximating thermodynamic equilibrium. So all of these dots here have sufficiently fast kinetics that, roughly speaking, they're what you would expect if we had actual equilibrium in the mantle. Now, as you slow down, so the color scale here shows on a log scale, the maximum reaction rate along that profile on a log scale. So these dots, as the reaction proceeds more and more and more slowly, the 410 gets displaced downwards and more downwards and more downwards, and it also gets spread out and more spread out and more spread out. So it's getting wider as it's getting deeper, but then something weird happens. You might notice there's this cluster of data points here, right? These obviously do not fit this trend. There's some sort of threshold effect that we observe in these models, where if the reaction is really extremely slow, if it's really extremely slow, then you're carrying metastable olivine so deep into the mantle and you're not reacting any of it, such that you reach a point where the thermodynamic driving force is so high and you still have so much olivine that everything just goes like that really quickly. And so now we have sharp transition, but it's displaced quite deep. That threshold effect is shown more explicitly in these charts. So on the x-axis now we've changed on a log scale to show the maximum reaction rate. Same here, maximum reaction rate. In this case, we're looking at it with respect to the width of the discontinuity and with respect to the displacement of the discontinuity. All of these dots here, notice that the width doesn't change. And same here, the displacement doesn't change. These are these dots here that I'm going to say are approximating thermodynamic equilibrium. So you're making it more sluggish, more sluggish, more sluggish. Nothing's happening, nothing's happening, nothing's happening, nothing's happening. And then once you get to this sort of intermediate range of reaction kinetic rates, you start to get this log linear relationship from here to here. And then suddenly you get all of these weird points here. So there seems to be two thresholds. There's a threshold where you're sufficiently fast that it's at equilibrium, right? We can just say it's at equilibrium. Or you're sufficiently slow such that you're having a sharp phase transition, but it's been displaced quite a long ways. And then there's this sort of intermediate range where as you decrease tenfold, for each tenfold decrease in the reaction rate, you get some linear increase in the displacement. You get some linear increase in the width. So there's this reaction threshold, right, that we observe in these types of simulations. Now, the plume story is actually boring, so we can just like whip right through it. Basically, nothing happens. Basically, the story is that even if you turn the reaction rate, even if you make it super, super duper sluggish, if you turn it all the way down and you make the reaction proceed very slowly, there is negligible movement. There's negligible displacement from what you would predict from thermodynamic equilibrium. And it's basically because, plumes are at an elevated temperature such that, the Arrhenius term sort of overpowers all the other terms. It's hot enough that it doesn't matter what the kinetic factors are, if it's dry or if you add water to it, it doesn't really matter. Even if you add a lot of water to it or if you make it super dry, the temperature is sufficiently high that the reaction just proceeds. It just goes, right? So this is the case for slow kinetics. The absolute slowest kinetics we have in any of the simulations And this is the absolute fastest kinetics we have in any of the simulations. And they're basically the same, right? You do have a slight bit of hesitation of the plume here, like for a moment, and then it just goes through. So the plume story is super boring. There is no scaling. There is no impact on the kinetics as it relates to the structure of the seismic discontinuity. Basically, nothing happens, nothing happens, nothing happens. I'm not sure what was up with this model and this model, but nothing happens, nothing happens, nothing happens. And then, okay, if you make it super duper slow, something happens. But notice the distance between here, 24 kilometers and 20 kilometers, is 4 kilometers. The minimum resolution that we can actually image seismic discontinuities is something like plus or minus 5 kilometers, right? So if you have plus or minus 5 kilometers to these things, they basically overlap. So this would be indistinguishable. We would have no chance of distinguishing between this reaction rate in Earth's mantle and this reaction rate if we were just looking at the seismic signals, in other words, right? So the plumes is like, what do you do about the anomalous plumes is the obvious open question, and I'm not sure. But for the slabs, we can show in our simulations that kinetics can explain things like slab stagnation. They can explain things like deep earthquakes from transformational faulting. In the case where you have sluggish kinetics and those things go down, 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 and then suddenly they react, you'd expect deep focus earthquakes there. And we can explain the variable seismic signals, meaning that sometimes you have a sharp discontinuity and sometimes it's slightly displaced upwards, and then other times you have some weak signal and it might be displaced downwards, right? So these weird edge cases where we would always expect this case, now these weird edge cases where it actually has a downward displacement and it might have a weak signal, we can explain those by, through kinetics. You don't need anything else. Well, the kinetic rate law includes water, so it does include water. And then for plumes, like I said, we cannot explain, according to our results here, these regions in the Earth where you would expect the mantle transition zone to be thinner, you'd expect the 410 to be displaced if it's slightly warmer, right? And then these regions of the Earth where it's slightly elevated, right? So the opposite trend. Kinetics can't, according to this rate law and to these results, like we can't explain those differences. So like there's something else going on there, And the last thing that I think is worth mentioning is these results sort of hint at maybe we can use seismic observables to estimate reaction rates in Earth's mantle. So if you go to regions of the mantle and you see that the depth of the 410 is actually at 410, you can sort of confidently say that, okay, we're within this range of reaction rates. It's approximately at thermodynamic equilibrium, and therefore it has a minimum reaction rate of somewhere in here. Now, if you go to weird regions of the Earth where you see these large displacements, these negative displacements, where you would expect a positive displacement if it was at equilibrium, and instead you have a negative displacement, you can say with some degree of confidence that, okay, the reaction rate has to be at a maximum, the reaction rate has to be here or below, right? So we have some maximum bound on the reaction rate in those cases, and vice versa. And then if you see really strange places where there's lots of deep focused earthquakes, you have a really nice result, sharp seismic discontinuity, but it's been displaced, then that would point to the, we're beyond this sort of really, it's like something strange is going on there. That would imply that the reactions are so slow, like weirdly slow, right? And so this would, I don't know, I guess raise a flag and say like, this is somewhere we should investigate more. Okay, so I'll leave plenty of time so we can have questions and then we can all just get out of here on a Friday. So far, because this work is ongoing, As I said, John hasn't even seen this because I've just sort of redone these models and the boundary conditions in the last few days. But so far, and by the way, the models that I ran before, the story was the same. It was modified slightly different because John's a smart guy and he gives me good direction, which is what you want. Okay, so the takeaway so far, the 410 is uniform in plumes. Okay, but slabs can show interesting dynamics and interesting seismic structures depending on the reaction rates. The kinetics in the case of slabs can explain these dynamics and unusual signals, but in the case of plumes, we can't explain it still. Something else going on. And then lastly, as I mentioned, this I think is what's going to lead me into the next phase of the project, where I'm going to start now in the next year, more and more working with seismologists at Cambridge University, who are also interested in this problem, who are actual geophysicists, who can teach me and help me understand what is the implication, as you displace and widen one of these discontinuities, as these teleseismic waves go, are they still going to bounce? Like, where is the bounce point? What would you expect in terms of the signals that you get in the receiver? All these sorts of geophysical, questions that I just honestly don't understand. Okay, but I think this is there is a really important implication that's shown by the simulations, and now I'm going to work with the seismologist to try to hone in on what that actually means in terms of real signals. And yeah, that's all I have to share today, so we'll just leave it there. Thank you.
So when you talk about fading,
Yeah.
is that when you're saying that the boundary is becoming more diffuse?
Just feedback. This one's working with you if you want to. Sorry, Richard.
When you're talking about fading, that's when you're saying the boundary is becoming more diffuse. There is such a sharp change.
Yeah.
So the ultimate of fading would be where the areas where you don't actually see any reflection at all, which there are some. So the lack of data is data. So have you been able to look at those and where these things happen and where they don't?
No,
Because there are seismologists occasionally go, oh, we can't see a reflection. Oh dear, oh woe is me.
Right.
But maybe that their lack of ability to see anything is data.
Yeah, so my general rough understanding of these discontinuities is, yes, if you diffuse that sharp contrast, then you're not going to get a strong reflector, and therefore you might just completely lose the signal. In that first map that I showed you, that seismologists have estimated the depth of these things, there was a fourth map in a different color scale, and it was the measurement of, it was the uncertainty in their estimations. And you notice that there's really low uncertainty where we have tons of receivers. And then there's really, really extremely high uncertainty where they're like in the Antarctic, for example, where there's almost no receivers. So yes.
Yeah, so that's the measurement uncertainty.
Exactly.
Reflection, but it's not uncertainty of, oh shit, it isn't there at all anyway.
Yeah, that's right. So we would like to, or what I would suggest to my colleagues at Cambridge is, I would ask the question, are there areas where we have good receiver coverage, where we have low uncertainty on the signal,
And they don't see anything.
and there is no reflector?
Yeah.
Right. Then we go to that region, and then we start asking the question, does it have something to do with the kinetics? And you start to try to understand the tectonics and all that kind of stuff. But yes, that's the direction of travel. Exactly.
Okay, I believe there is, and if I'm right on that, you're going to make them very happy because they can sit there saying, why can't we see it? It's screwing up. So,
Right. Okay.
happy seismologists.
Great question. Yeah, great question.
Well, time we were
That's a really interesting talk. So could you go back to the where you were showing the displacement with the rates, slabs. Right. So is that displacement in absolute terms? I think it's displacement of 410, but is it of the discontinuity or is it from 410 kilometers depth?
Yeah, good question. So what we actually do, imagine this is the center line of the model, this is the surface of the model. This is the bottom of the model. The reaction happens nominally at 410 kilometers here.
Yeah.
But as you start to react and form more wadsleyite, the question is, you know, where do we measure, how exactly do we measure the width and the displacement of these things? In the simulation, I go down this line and I say, find the depth where we have 90% olivine, and then find the depth where we have 90% wadsleyite.
Okay.
And that's what
That's
I'm going to
ridiculous.
define as so the width of the discontinuity is defined by the depth at which we've reacted.
Okay.
Let's say we reacted 10% of the olivine, and then the depth at which we still have 10% of the olivine left, so it's become 90% wadsleyite. So let's say the reaction is completed from here to here. That's the width. And then the depth then would be the depth at which we have 90% wadsleyite relative to the nominal 410 depth. So that's how we get our
That's the
displacement.
width, but your displacement is then an absolute depth, though, or relative to an absolute depth on that.
Yes, it's relative
Right.
to the nominal 410.
Because this is, it's very sort of anti-canonical then, this, isn't it? Because the 410 is supposed to go up, right, with the slab. And there you've hardly got it going up at all.
Yeah, so from here to 0, so this is the nominal.
Yeah,
And if you're in a cold regime, you'd expect it to go up.
yeah.
So this has been displaced by some tens of kilometers in the upwards direction. So this is what you
But that, as you say though, that's barely detectable with seismologically, right?
Well, they tell me 5 kilometers is what they can resolve. So there's lots of studies that suggest that, for example, beneath Central Europe, my colleague at Cambridge did some work on this, and they have fluctuations on the order of plus or minus 30 kilometers.
Okay.
So this is definitely something that they're so confident, like, no, there is a topography, there is definitely a displacement here relative to the nominal 410. That's what they can see.
But that is very minor compared to then your huge displacement to deeper ones, which is
Yeah.
completely the opposite of what
That's right.
many of us have been teaching for a long time.
Well, that's right. So what does that imply? That implies in the Earth, you're probably closer to equilibrium than you are to this state, which may not exist,
Okay.
which just implies because we sort of constrain our rate law based on the empirical data sets that come from the experimental petrologists. So they're doing stuff in the lab, they measure the rates, they're measuring rates in the lab. And of course, we have to extrapolate these things. So the errors, the uncertainties that they have in their rate logs span several orders of magnitude. So there's definitely areas within this chart that are for sure probably don't exist on Earth. So it's giving you some ballpark, like, yep, if we see a signal and it's 30 kilometers above 410, we're probably here. We don't see any signals where the 410 has been displaced 70 kilometers, right? So this just implies that these reaction rates, they just don't exist in the mantle. That's how I would interpret that.
So what you're saying is all the cool stuff you told us isn't there. That's a bit impressive.
Well, yeah, either it's not sufficiently dry or it's not sufficiently cold.
So it provides its absence provides an extra constraint, but still it's impressive.
Yeah.
But I mean, so just to follow up to one thing then, you mentioned some places where it doesn't quite work, like Cascadia and the Caribbean. So is there any, like, off the top of your head, reason why there you should be further to the left of your figure?
Well,
the slower bit.
Yeah, in those cases, so in Cascadia, the mantle transition zone is a bit thinner than what you could expect. Of course, the Cascadia slab is not as cold as other slabs. So that's one thing, but you still expect a positive displacement and not necessarily negative displacement. So based on this work, and there's lots of different hypotheses, right? So we can discuss some of these things, but just based on these results, I would suggest that, let's see, and this is starting to, I was going to say, I would suggest that the reaction rates are sufficiently slow so you get a negative displacement, but that's a bit contradictory. We know something about the tectonics of the region, right? It's very close to the ridge. We know that the plate itself is young. So does it make any sense that the reaction rate would be slower than, for example, the slabs in the West Pacific. No, that doesn't make any sense. So this can't explain everything. I mean, there's still gonna be some anomalies that are head scratchers. It's like, yeah, it can't explain everything, I think. Yeah.
So I'm gonna basically ask a question that was asked last week, but I think it could be interesting given that you've got this, you're showing this stuff promoting pooling, right? Is there a plan to do this for 660 in the future?
Yeah.
Okay.
Yeah, in fact, the seismologists were really kind of dismayed, I think, every time, like, we sort of went on this track. John mentioned there's some good reasons why we stuck with the 410. But the seismologists were more interested in the 660 because it shows more topography and you have better signals. So the 410 is usually, yeah, not quite as strong, and it's also doesn't have this, like, really large deviations in it either. So they really want us to do the 660 too. So I mean, we're gonna go there.
I guess what's the extra challenge associated with doing that?
Well, in my case, in Lucy's case, it's the fact that you don't have what's the word, John? Polymorphic. You don't have a polymorphic phase transition, right? So you're not just going from olivine to something that is olivine, same chemical composition, but just has a different structure. You're going from the dense phase of olivine, bridgemanite, or from ringwoodite rather, to bridgemanite and periclase. So then you have to, in Lucy's case, we were looking at the micro scale. Now you're considering, instead of a two-phase system with the same chemical composition, you're considering a three-phase system with the same chemical composition. In my case, I don't think there's really any barriers to jump right in, because we have, all we need is thermodynamic data for these phases, which we have. Well, we also need some constraints on the rate factors as well in that equation, which is a lot of data for olivine and wadsleyite and less for the other reaction. So that's the main reason. Larry?
I'll just talk loudly.
Sure.
So just to help visualize this, if your reaction takes, let's say, 1 million years, which seems reasonable, looking at, how far could the plume transport in that time? How does that correspond to in terms of a distance?
Yeah, it's a great question. The models that we have are pretty dynamic, meaning that we only impose pressure and velocity conditions right at the boundaries. And so everything else is free to flow as it will. Now there are ways to increase let's call it the advection or the convection rate, the transport rate of a plume or a slab, right? By just, forcing it down with a bit more force up here. But we don't have full kinetic control of that. But it obviously does play a part when we're talking about the structure of the seismic discontinuity, right? Because if you have moderately sluggish kinetics and the thing is also moving very slowly, then that's going to be different than if you have moderately sluggish kinetics but the thing is moving very quickly. In the latter case, it's going to transport metastable olivine deeper into the mantle. But then again, at some point, we see here, you can only go so deep in the mantle. So there's sort of like a maximum threshold where even if the slab is moving really fast and it's really cold, so you would expect metastable olivine to go really deep. These results suggest the thermodynamic driving force becomes so great that it really can't get further than 50 kilometers away from the 410. It just can't. Doesn't matter how slow you make the kinetics. The thermodynamics say we're ready to burst. It's like we're ready to make wadsleyite. Switch gets split. And the switch gets split, right? It just like overpowers the sluggishness of the kinetics. So yeah, I would expect that if we fiddle around with the velocities and things, we would run into, I don't think we'd be able to get much deeper than this, to be honest.
But you've already said that isn't happening anymore.
Right. Right.
Yeah, so kind of following on from that a little bit too, I'm just interested in the model that you're using, the aspect model. Are there any kind of real logical discontinuities in there? Does the I mean, you showed with your equations to start with, you've got buoyancy, density differences in there as well. And I was just wondering whether there was any rheology and change in rheology across the discontinuities as well, which might feed into these things too.
Not in our case. Of course, you can do that. You can do all sorts of things with the rheology. The rheology is very simple. It has a temperature dependence to it, and that's it. Otherwise, it's viscous Newtonian, and it's the same for the wadsleyite or for the olivine and the wadsleyite fields. And there's, you know, the question is, you know, should we be changing the rheology? Is there a large contrast between the rheology of, you know, an olivine rich rock and a wadsleyite rich rock? The rheology is probably about the same. But in the slab, right? In the slab, because it's cold, it should be behaving as stiff material. And if you were to use a different type of rheology, like a pressure, strain rate, temperature dependent, viscoplastic type of rheology for the slab, then the dynamics would definitely change. Yeah, they definitely change.
So, yeah, I mean, I guess it was just a question about how much it might explain some of the anomalies that you see. But first of all, I really liked your talk. It was beautifully explained as well. And I think just isolating just the kinetic effects, are definitely the way to go. I mean, anybody can make a model with boatloads of free parameters. You can vary everything and you can produce everything you want. So I think, you know, just in terms of isolating one process, it's really nice. And obviously, maybe rheology and things like that can come into the discussion. But
Yeah, that's right. That's the approach. Yeah, thanks.
We'll do one more up here, and I'm going to see it. I'm finished. Yeah.
Sorry, I've got a bit of a technical question. For your thermodynamic, for your kinetics, are you using some form of numerical solver for that? Or how are you like calculating that?
Yeah, it's a good question. It is technical. Let me try to boil this down. There's a field in the background of the model that's distributed everywhere that tracks this big X parameter, which is the volume, how much wadsleyite or how much olivine is there. And that field itself indexes around. And at each time step, you go to what they call this operator splitting, where we solve the general advection equation, like let's say the large scale equations, and then we go into a separate time step, a smaller time step that we iterate over within the larger time step, to calculate the reaction, how far the reaction proceeds. Because at each time step, we calculate the reaction rate, right? And so then we have to integrate that over the small time step to see, okay, we start with this much wadsleyite, we know what the reaction rate is, then it goes into the smaller time step and integrates that over these little small time steps, so that by the time we get to the next time step, we then have this X field updated.
So you're using something like Contera or Camkin or something? Like
That's, so okay, now you've gone over my head. Yes, that's a question for the mathematicians who work on the solver, which is a great question. If you're interested in that kind of stuff.
So should I be able to find that on the aspect? So
Yeah. Absolutely. And people at the hackathon, there's a range of people from structural geologists to people like me who have a petrology background, geodynamics background, to like really hardcore mathematicians, pure mathematicians who work on the solver itself.
I'll do that. Thank
If
you.
you're interested, yeah, go check it out and talk to the aspect folks because they're really friendly.
So your last one from you, Sina?
Yeah, it's also a very specific question. I can't remember, did you show at the very beginning of your talk, did you show the reaction, the relation of the reaction rate and the dynamic pressure, dynamic temperature? I was just wondering, do you constrain those reaction rates based on experiments, or is there any is there any factor this?
Yep, so, let's see here. Delta G, so this term here, comes from thermodynamic data. This P and T, everywhere you see a PT, that comes from the numerical solver. So everywhere there's a pressure and temperature, that's from the numerical solver. Delta G is from thermodynamic data, and then all these Z terms, these come from the experiments. Except for grain size. Grain size is sort of a free parameter that we can play with, but A, this constant, these constants here, and also the activation enthalpy and the activation volume. All of those are come from the.
So the
from
dynamic
experiments.
pressure and temperature do affect the reaction rate. In which direction?
Yep, they do. Yeah, so let's see. If you have, if you increase the pressure, so if you are squeezing the rock more than it would be under hydrostatic conditions, you're increasing delta G. Well, it depends also, so the sign of the increase or decrease depends on the difference in the molar volumes of the mineral. So if you're considering
Yeah.
forward reaction or the back reaction, then the sign's gonna flip. So like for the case for wadsleyite, if you squeeze it a little bit more, you're going to decrease delta G. You're gonna promote the reaction to go towards the wadsleyite, right? And I'm not exactly sure about their enthalpy, so I won't go there.
Yeah, because based on my grain scale simulation, I have one observation under unhydrostatic hydrostatic stress condition, increasing the differential stress. It's not your dynamic pressure, but it's okay.
It's different.
Because I observe increasing differential stress will slow down the reaction rate. So I just wondering if they have some, okay.
Yeah.
Thank you.
Thank you very much again.
Yeah.
Round of applause for